So this is a star. It's collapsing, and basically, it's a conservation of angular momentum problem where they're asking us for the final angular velocity, such that the thrown-off mass has no angular momentum, and the thrown-off mass has 3/4 of the initial angular momentum. So we should first just write down our givens. So we'll say the mass of the star, we'll denote it as S, equals 8 times the mass of the sun. And the radius of the star equals the radius of the sun. We know that the angular velocity of the star in its revolution is 1 revolution per every 9 days. The mass of the star final equals the mass of the star over 4, or simply 2 times the mass of the sun. The radius of the star final is going to equal 12 kilometers, or we should convert to 12,000 meters. Now, essentially one thing that we should find in this case would be, well, first of all, we should apply for part A, apply the conservation of momentum. So thrown off mass has no L, angular momentum. So Li equals L final, and that means that I initial, omega initial equals I final, omega final. So that means that omega final equals omega initial, I initial over I final. Now, I initial is going to be equal to 2 times the mass of the S times the radius of S squared all over 5. Or we can say 16 times the mass of the sun, radius of the sun squared divided by 5. I final is going to be equal to 2 times the mass of the sun, of the star, times rs, the radius of the star, final over 5, or 4 mass of the sun, radius of the sun squared, or sorry, this is not the radius of the sun squared anymore. This would actually become 12,000 squared. Divided by 5, once again. And I initial over I final, if you were to simply divide these, you would actually get to 4 radius of the sun squared divided by 12,000 squared. Again, these 5 cancel out. The mass of the sun cancels out. 16 divided by 4 equals 4. That's how that's accounted for there. The radius of the sun is here, and then 12,000 would be left as a denominator. So at that point, we can just say that omega, we'll just separate this a bit. Omega final equals 1 revolution in 9 days times 4 times the radius of the sun, 6.957 times 10 to the 8th squared divided by 12,000 squared. And this would be equal to 1.494 times 10 to the 9th, and this will be revolutions per day. So this would be your answer for part A. This is the revolutions per day after the star has collapsed and the thrown off mass has no angular momentum. Now for part B, it's a little bit different because the thrown off mass has L equals 3/4 of L initial. So the thrown-off mass has an angular velocity of 3/4 of the initial an angular momentum of 3/4 of the initial angular momentum. So we can say that Li equals L final plus 3/4 L initial. So that means that L final simply equals Li over 4. Now, you could do this. But if you realize that L final here equals omega initial I initial over I final, and you're simply dividing this by 4, wouldn't you be able to just divide it by? Well, you can just divide the entire thing by 4. So we can let's write it out to prove it though. So we can say I final omega final equals I initial omega initial over 4. So that means that the omega final equals I initial over I final omega initial over 4. Now, doesn't this look very similar to this? Yes, essentially, you're only adding a factor of 1 over 4. So this right here looks exactly like this, except that we have a 1 over 4 as the factor. So essentially, you can simply just take this divided by 4. So it will be 1.494 times 10 to the 9th divided by 4. And this is going to equal 3.735 times 10 to the 8th revolutions per day. So this will be your answer for the second part, such that the thrown-off mass has 3/4 of the initial angular momentum. And that's the end of the solution. Thank you for watching.